Alright, so ladies and gentlemen, here we go. So, this chapter, Thermochemistry, just so you are aware, is going to be combined with another chapter. Alright, so this next set of material is going to be a double set, okay, just like the one we had previously. And it's on thermochemistry, thermodynamics. And guys, anytime you see the prefix thermo, alright, I want you to think heat or energy, okay? And that's what we're going to be talking about here. And at the beginning of this chapter, guys, you are given some laws of thermodynamics. And this first one is going to look familiar, or should look familiar to you. Okay, it's the law of conservation of energy. The reason I say that should sound familiar is because we have seen a law of conservation of mass before. And if you think about what the law of conservation of mass said, it's that mass cannot be created or destroyed. And that's exactly what this says. You cannot create energy. You cannot destroy energy. Alright? All you can do is convert it from one form to another. Alright? And let's just throw out some ideas. Just from your general knowledge of life. What are some different kinds of energy that you hear about? Throw some out.
Nuclear.
Okay, nuclear. Solar? Solar? What else? What else? What else? Nuclear, solar. Yep. Geothermal. Yep. Mechanical. Kinetic. Yep. Chemical. Yep. Electrical. I mean, there's tons. There's all kinds of energy out there. All right? And guys, in all honesty, most processes in life, doesn't have to be a chemical reaction, most processes of any sort are really just converting one form of energy to another. And here's a sort of deeper thinking, more philosophical way to think of this. The energy of the universe is constant, right? Meaning, you cannot create energy, you can't destroy it. There's a finite amount, all you can do is change it from one form to another. Now, as we said, there's lots of types of energy out there. We, however, in here, are going to focus on primarily two types. Potential being the first one. And most of you in here are either in physics currently or you have taken physics. You hear about potential energy in physics a lot, but it's in a very different kind of context than the way we're going to talk about it. Okay? In physics, I remember we did a lot of problems where, like, a person holds a bowling ball over the side of the Empire State Building, which, by the way, is illegal. Okay, so don't do that. But it would say, you know, calculate the amount of potential energy that this bowling ball has, which is a lot. Another way, another more physics way to think of potential energy, okay, and I always think of this because on my drive to work every single day, I drive over the top of a dam, okay? Anytime a lake is created, so it's not a natural lake, it's a man-made lake, those are usually made by damming up the water, holding the water back, okay? And what's on one side of a dam is usually a lake, and then what's on the other side is a pretty steep drop-off. The water in any kind of man-made lake has a great deal of potential energy. I almost think of it like the potential to do damage, okay? Like if that dam were to wash out, that would be a huge amount of energy that water would be carrying. If you dropped the bowling ball off the side of the building, which you're not going to do, that would cause a lot of damage. But these are very physics ways to think about this. Here's how we are going to think about it in more of a chemistry setting. And this is a great example. Saturated fat. All right, well, you may or may not know, but fat molecules, and there's different kinds, but the general shape of any kind of fat molecule is just very, very, very long carbon chains. Okay? Now, other things that we eat that have a similar structure, carbohydrates, sugars, all of these things are made up of these long carbon chains, proteins as well. But I want you to think about this word. All right? Take yourself out of chemistry. Put yourself in your English class. If you came across this word, saturated, can you give me like a synonym for that word? Saturated? Yeah. Full? You know, to capacity, can't hold anymore? Well, when we say saturated fat, this carbon chain being, quote, full of what? Well, it means at every available place, this carbon chain is full of hydrogens. Okay? I'm not going to draw them all in, but that's what that means. Saturated fat means carbon chains that at every possible location have a hydrogen. They're full of hydrogens. Okay? Now, saturated fat gets a bad rap. All right? You always hear, you know, these nutritionists, they come on, you know, Good Morning America and, you know, the Today Show, and they always talk about how saturated fat is killing us. And, you know, the American people, we're all obese and we're all going to die of diabetes. And, you know, saturated fat is the bad guy. It's all to blame. All right? And I'm not saying that's not true. Saturated fat is not good for you. However, from a purely energy standpoint, ladies and gentlemen, saturated fat is loaded with energy, and that's a good thing. Okay? From an energy perspective, from a nutrition perspective, not so great, because this leads to like hypertension and you know, diseases of the heart. It causes blockages. It's not good. Okay. So can you guys give me something, some kind of food that you know has a ton of saturated fat? Something that,
I don't know.
Something, how about a Krispy Kreme donut? Which is a weakness for me, by the way. Okay? Like, I could house a dozen of those Krispy Kreme glazed donuts in like a minute. Okay? They are delicious. Unfortunately, they are loaded with this. Alright, so let's say you eat a dozen Krispy Kreme donuts. I can't think of anything better. This is now swimming around in your stomach. What does your stomach do to things that you eat? It digests it. And what does digestion really mean? Breaking it down. Breaking these bonds. Okay? And saturated fat has a lot of bonds. There's energy stored in all these bonds. If you have a lot of bonds, that's a big source for energy. Now, the thing is, though, to break these bonds requires energy. So if it requires energy, that sounds like your body is having to expend energy to digest this, and that's true. But all of these pieces go to create. See if you remember from biology. Do you remember this thing? It's like the fuel of your cells, the fuel of your body. These things go into the process of creating ATP. Does that ring a bell? Sort of? Okay. ATP is like the fuel of your body. All right? It's your energy source. Does anybody remember what ATP stands for?
Oh.
Okay, what was the first word? Yeah, adenosine triphosphate. Very good. Okay, so saturated fat, huge source of energy, huge source of potential energy. Now, if you are, listening to this lesson here, I don't want you to think like, oh, I'm about to go run a 5K this weekend. I think I should probably house a dozen Krispy Kreme donuts before that race. No, don't do that. Okay? From a purely energy standpoint, that would be great, but there's other things at play. You're going to be barfing around mile 1, so don't do that. Okay? But this is what I'm talking about. There is potential energy stored in these bonds. The other type of energy that we're going to concern ourselves with is kinetic energy, the energy of motion, movement. Right? Again, guys, in physics, you're going to be talking about this a lot with problems like, a grocery cart gets away from you and the grocery cart is moving down a hill at such and such velocity. We're not dealing with grocery carts in here. We are dealing with the motion of atoms, molecules. Okay? Do you guys remember the definition of temperature? Thank you. The average kinetic energy. Kinetic energy in chemistry is tied to temperature. And on your equation sheet, ladies and gentlemen, this equation is on there. You will use this equation in physics a lot. You know what V stands for? Not volume.
Velocity.
Velocity. Okay? Now, in all honesty, in my 12 years of teaching this course, I've never had to use this equation. I'm not entirely sure why it's on there, but it is. Maybe there will be some time that you need to use it. This is mass, this is velocity, okay? But again, we are going to talk about kinetic energy more in terms of temperature. Okay? Now, I want to make sure that there is something here that is abundantly clear. These words, temperature and heat, people think that they mean the same thing, and they do not, ladies and gentlemen. Okay? Temperature and heat are not the same thing. Temperature, as we just said, is the average kinetic energy of something. If you raise the temperature, all you're doing is causing these particles to move faster at higher velocities. Heat does not mean how hot or cold something is. That is not what heat means. Okay? Heat means energy. And it's really a flow of energy between two things. Okay? Two things that are at different temperatures. Okay? And we're going to do a little experiment here. Whether you are sitting in a chair or a stool, doesn't matter. I want you to reach down and touch the metal leg of the stool or chair you're sitting in. Does it feel hot or cold to you? Okay, it feels cold. Is that because it is cold? No. Well, what kind of temperature should it have? Room temperature. Why does it feel cold? Because our bodies are warmer. Okay? So think about it, guys. Which makes more sense? If heat is involving a flow of energy from one thing to another, do you think heat flows from hot to cold or cold to hot?
Hot to cold.
Hot to cold. Okay. So your hand is warmer, so your hand is losing heat. Would you agree? And where is it going? Into the chair. All right? Well, what I want you to do now is feel the skin where you were just touching that chair. If you need to, touch it again, go for it. Okay? Feel your skin there. Your skin feels a little cooler, doesn't it? You know why? Because your hand, that part of your skin right there, just lost heat. So it should feel cold. Right? So heat always flows from hot to cold. And some words that you're going to see us use a lot are the system versus the surroundings. Okay? When I say system, okay, what I mean is the thing that we are focused on. In most cases, guys, in here, what I'm going to refer to as the system is a chemical reaction, most of the time. Everything else is called the surroundings. We are part of the surroundings. Okay, so for example, in this, what we just did, we held the leg of a chair. Let's consider the leg of the chair as like the system, and how we are interacting with it. We are part of the surroundings. Okay? And when you put those two things together, again, very like deep philosophical thing here, you put those two things together, you get the universe. Okay, I know. Now, this next part, this is where we're going to get in some review from actually what we covered last class. Endo versus exo. Right? All reactions are one of these types. All reactions are either endo or they're exo. Okay? It depends on how the heat is being exchanged. Okay, so let's just review, because we've seen these terms before. We talked about these terms last class. Exo, heat is flowing out of the system, leaving the system, exiting, being produced. Think about last class, ladies and gentlemen, when we saw exothermic reactions. Did we write in the word heat on the product side or the reactant side? On the product side, right. Okay, now let's think about this for a second. Okay, let's imagine in my little travel mug here, now this usually holds coffee, but let's just say there's a chemical reaction going on in here. And I tell you that it's an exothermic reaction. And I put my hands on it. The system is what's inside my travel mug here. If heat is flowing out of the system, would this feel hot or cold to my hands? It would feel hot. Heat is leaving the system, and where is it going? It's flowing into my hands. Remember, I am part of the surroundings. So exothermic reactions, ladies and gentlemen, feel hot to your hands. And it doesn't even have to be something you're holding on to. If I had a thermometer in there, a thermometer is part of the surroundings as well. We would see the temperature going up. Okay? Exothermic reactions feel hot. Endo. Okay, this prefix endo basically means into. Heat flows into the system. Heat is absorbed. Heat is required. Right? Think back to last class. We talked about Le Chatelier's principle. Shift right, shift left. You know that a reaction is endothermic. Where did you write the word heat? On the reactant side. Okay. Let's come back here. Now, it's a different reaction in here. And I tell you this time that this is an endothermic reaction taking place in here. You put your hands on it. This one we said is going to feel hot, so this one is obviously going to feel cold. Okay, but tell me why. Okay, this reaction is absorbing, pulling energy from the surroundings. In this particular case, if I have my hands on it, where's it coming from? Yeah, the heat is coming from my hands. And ladies and gentlemen, think about it. If your hand is losing heat, just like we were holding onto the leg of our chairs, if your hands are losing heat, it will feel cold. Okay? That can be a little confusing. But the point is, guys, in this thermochemistry section, you're going to be given multiple situations where either they tell you something feels hot or cold, or they give you some temperatures, and you have to figure out whether the reaction is endo or exothermic. Here is one final way that you might be given information. Let me break this down for you. All right, this is something called an energy curve. You'll notice on any energy curve, you have reactants on the right-hand side, and your products, on the left-hand side, your products will always be on the right-hand side. Would you guys agree that this graph is, in general, downhill in shape? Would you agree? Okay. In general, it's downhill. Well, ladies and gentlemen, this is an energy curve for an exothermic reaction. Heat is leaving the system. My reactants had a certain amount of heat, and I lost some. It left. It was released. So now I have less energy. Okay? And tell me one more time, guys, would this feel hot or cold to my hands? Hot. Heat is leaving the system, and where is it going? It's going into your hands. Here's why this can be confusing sometimes. People forget, I should say, that this is an energy curve, and they think that this is a temperature curve. It is not. Look what's on the y-axis. Potential energy. It doesn't say temperature. And even if it did say energy, guys, how do you measure temperature, the average? Kinetic. That's not what this says. This is not a measure of temperature. I'm going to put some numbers on my y-axis here. I'm going to say this level is 12 kilojoules. Kilojoules or joules, that's just a unit of energy. And this level is 3 kilojoules. Now listen carefully to what I ask here. I want you to do a subtraction. Heat of the products minus heat of the reactants. What do you get? Negative 9. Okay, negative 9 kilojoules. Ladies and gentlemen, maybe this will look familiar to you. That's a delta H value. We saw this last class. This was one of the ways I could tell you if a reaction was endo or exo. And last class I said, if a delta H value is negative, that indicates an exothermic reaction. And guys, that's where these numbers come from. It's from these energy curves. Okay? But in general, if you see a downhill energy curve, that means exothermic. So what would endothermic be then? Uphill. Like that. Reactants are still on the left. Products are still on the right. Endothermic, heat is being absorbed by the system. I had a certain amount of energy. I absorbed more, and now I have more. Again, let's put some numbers to this. I'll choose different numbers this time. Can you tell me, please, energy of my products minus energy of my reactants, what number do I get here? 8. Positive 8. Last class we said a positive delta H value indicates endothermic, and this is why. The take-home message here is, ladies and gentlemen, you will be given a variety of ways in which to determine whether something is endo or exo. Maybe it's a graph. Maybe they give you some temperature information. There's a variety of ways. I'm going to stop there. Yes?